So I will be speaking on behalf of the Gyselalib++ team. The idea of this talk is to present, so we are in the algorithm section, but it's more about presenting the code and where we come from and what we have, where we are going. So Gisela Fortran, so this is an old code. It's been 15 years since it started producing science. This is a 5D, so 3 dimension in space and 2 dimension in speed, plus the species simulation code. And so we try to model the plasma in tokamaks. So you can see a slice of tokamak there, for instance. So this is quite unique on the numerical side of things. But when it comes to computer science, it's actually quite simple. So there is OpenMP, MPI, and some I/O libraries. So it's not that big of a code, but it consumes a lot of CPU hours. Unfortunately, it's able to scale quite well, even on very large amount of cores. So this is where we come from. But then Exascale is coming, and unfortunately, this code, which works very well on CPU, is well tuned. So a lot of people, very smart people, have spent a lot of time working and optimizing this code. Unfortunately, it doesn't work as well as we hoped to on GPU. And we want to use the new machines, especially to do larger simulation, such as, for instance, the ITER tokamaks. And there is also the fact that we want to add new physics into the code, and incremental changes to the old code was not possible anymore because they are way too involved. We would need to rewrite basically all the code. So yeah, we want new physics, we have new hardware, and how do we go forward? So we tried porting Gisela Fortran. It was done 3 years ago. We tried using OpenMP offloading, and it works, let's say, not as expected. So we had compiler issues, we had segfault, spurious crashes. It was hard. And one of the most inefficient issues was that even if we could port the code, what would work best on CPU would not work best on GPU. And we had, in the end, a lot of algorithmic issues. And just porting the code as is, so just adding the OpenMP target clauses, for instance, was not enough. One of the big bottlenecks, so eventually we did port all of the things, but one of the big bottlenecks was the collision operator. So I'm not going to go into the details of this operator, but it was taking almost all of the time, and it's one of the most time-consuming operator, and actually one of the parts in the code that was the most tuned over the years. So yeah, what works best on CPU is not necessarily what works best on GPU. And so we ended up rewriting this operator. So we used Kokkos and Kokkos kernels, and only that. We didn't want to have many dependencies. And using a C interface, we are able to provide that fast implementation on GPU on both the Gisela Fortran code and then the new library, which I'm going to present next. Looking forward, there is some issue that we still need to think. So we believe there is some opportunity for kernel fusions, which should be quite easy to do, and also to do some cache blocking. And maybe having some way to do that in Kokkos directly in an efficient way, and potentially, depending on the hardware, which Kokkos will end up targeting, it will be easy. It will be good. That's it. And so quickly, some performance numbers. So the roofline looks pretty great. And using this ported operator, now we are able, using the old Fortran code and OpenMP offloading, to achieve speed up to 4 on nearly real case scenarios. So this was done comparing the same amount of nodes on the same cases, but varying the hardware that we use. So either MI250X, 300A, or the Genoa nodes on Adastra. And so we have a code that works reasonably well, starts to be viable, but is Fortran. But we didn't fix the issue of adding new physics to it. And so this is why Gisela++ exists in a way. So it's very modular. Basically, you can view this library as a collection of operators for gyrokinetic simulation for tokamaks. It's based on DDC mostly, of which Thomas Padiolo talked about yesterday. And then the key idea is to have a simulation, so at the bottom, which will reuse and compose the operators of this library. So instead of having one big monolithic code, we have many simulations that makes use of that uses this library. This also helps with testability because the composability helps a lot. So quickly on DDC, basically it allows you to avoid mixing quantities that should not be mixed, and it also provides a way to iterate over the fields without bothering about the indexing. So to conclude quickly, so a few requests to the Kokkos community. So we have gone already way too much around on that fact, but we need some way to collapse iteration spaces so we can use properly all of the lanes of the GPU. So this would take place probably in the team MD range and the MD range policy. Also a need for a vectorized libm, so there is Kokkos-Sim, so there is some hope around that. But currently, the exponential function, for instance, or the sinus, cosinus, etc., all of these functions are not vectorized, as far as I know, or at least we rely on the compiler to do the auto-vectorization. And so this is not, this is an issue. Also, I believe there is code that is duplicated between a Kokkos batch vector and Kokkos-Sim, so maybe merging that will be interesting. There is also the issue of avoiding redundant indexing calculation. So as far as I know, this is going to be fixed in Kokkos 4.7 using MD span and the mapping that you can get out of the MD span. And then you can reuse the index calculation on many views. So I don't know how to do that, but maybe adding a way in Kokkos to do better tiling and operator fusion. So these two features, I believe that if we have tiling and operator fusion, we can have a single code that will work very, very nicely both on CPU and on GPU without changing too much the algorithm. Or at least that would be hidden into Kokkos. And obviously, a little bit of documentation would be nice. So yeah, a few challenges and insights. So be very careful because modularity versus intranode performance versus internode performance is not the same. So you need different algorithms to do different things. So yeah, try to see what are you targeting. Do you want to scale on all the machine? Then you may not use the same algorithm as if you want to use a single node very efficiently. And often, unfortunately, when you want modularity, it ends up costing you performance. So be careful with that. The Fortran version was very efficient, but it was also not flexible. This is for the same region. It was not very modular, but it gave a lot of performance. And it was able to scale on all the machine, basically. C++ is very versatile, but it's very hard to use by physicists, and I don't really know how to fix that. But this is an issue. We are using DDC, which is basically a strong typing library. So this has a productivity hit, for sure, but the hope is that for the long term, it's going to be a gain. At least we will hope. We won't mix quantities. And so because Gisela has a large team and there is a lot of people that are very different backgrounds, it is necessary for us to provide a way to catch common mistakes. And so this is why we have a very involved CI with a lot of testing, code convention, best practices, and a lot of stuff around that. And also we force the user to write documentation. And we hope that by doing that, the code quality will be maintained and people won't fear as much modifying the code. Unfortunately, doing that also costs, it has a lot of overhead. And that's it for me. Thank you.
All right, let's have our next speaker come up while we take any questions. Yes, sir.
Thank you for the presentation. I have a question. So do you end up, for critical kernels, do you end up having still a separate implementation for CPU and GPU?
No, we don't.
Okay.
Currently, we don't, and we still get good enough performance.
Okay.
But the main issue is vectorization of the transcendental function, so exponential. This depends way too much on the compiler to be done correctly. And on CPU, this is 4 to 8x performance penalty.
Okay. Thank you.